welcome to Unit 8. We're going to be talking about electric potential, voltage, which is electric potential, and capacitors in this unit. But we're going to start with Chapter 24. We're looking at electric potential. But to get an idea of this, let's think about gravity and gravitational potential energy and what that is. Gravitational potential energy we calculated as mgh. And so if we talked about gravitational potential, just without the potential energy, but gravitational potential, what we could say is that's the energy, gravitational potential energy per unit of mass. So if I took this, this is U, but gravitational potential, which is not a thing, but let's imagine, that would be U, the amount of potential energy there is per mass that's there. So that would be mgh over m, so that would just be gh. And notice then that would be the same for any object. You could say the gravitational potential of anything that's raised to the same height, those would be, they have the same gravitational potential. And so that's kind of like what we're talking about here with electric potential. It's the idea that it's the amount of electric potential energy there is per unit of charge. Okay. And so let's think about that in terms of work done, right? Potential energy is like work. Work is force times displacement, right? F delta x. And we're back. Okay. So this is the amount of work done, right? Remember, work is also the negative of the change in potential energy. Keep that in mind. Use that. And so what's the electric force that we're dealing with here? Well, the force is a result of a charge in an electric field. So work is equal to QEX. And so this is also equal to the change in potential energy. So it's equal to the negative change in potential energy. Another thing to look at here is the fact that if I have a box and I lift it this way, the only thing that matters is the vertical component here in terms of gravitational potential energy, right? Same thing for an electric field. If I have an electric field that's up and I'm moving some charge through that field, like a positive charge that way, the only thing that matters is the upward component of this motion. So what we're talking about is a dot product, the dot product between the force and the displacement there. And so we can see that negative delta U is Q, and then remember, formally, we have the integral f dx. Well, this is the integral Q. Q is constant, so E dot ds. S is going to be just the path, or whatever it is. So then delta U over Q is equal to negative integral E dot ds. This is our definition of voltage. Voltage is the amount, negative change in potential energy per unit charge. And so 1 volt is joule. It's a joule per coulomb. Those are the units on that. So all right. So then here we have some illustrations. Positive charges. If a positive charge is moving in the direction of the electric field, so like this, right? Here's the electric field. Positive charge is moving in that direction. Then the field does positive work on the charge, and the potential energy decreases. See, now this is where it's going to get confusing. Is potential increasing, decreasing? Because now we have positive and negative. Here, if I have some positive, some positively charged object, right? It's got pluses all around. The electric field looks like this. Here, the voltage is high if I'm close, because here's where I have the most potential energy. per charge. But if I have some negatively charged object, this is a low potential energy. And actually, this is positive potential energy. This is negative potential energy, or electric potential. Because any charge, the place where it's going to have the most potential energy near this is when it's far away. Getting closer, it's losing potential energy. So the change in potential energy depends on the charge of the object and the thing that's creating the electric field. Okay, and so in a uniform electric field, so now we're on to the slide after those two circle things, 24.3. Electric potential is a way of simplifying a system of charges. If I have a bunch of charges, I can simplify it this way rather than thinking about the potential energy that's actually there. And it's a scalar quantity, so we don't care about the vectors, the direction. But it depends on the distribution of charges in space. And like gravitational potential energy, here we're going to set this 0 at infinity. And so delta, the change in potential energy, is UV minus VA. This is the potential energy at B minus the potential energy at A, all divided by Q. So it's UV minus potential energy at A over Q. All right, we're looking at the change in potential from one place to the next. So this is going to be negative Q EX over Q. So that's just negative EX. Because this is the change in potential energy, so it's the negative of the work done, right? This was the work, QEX, per unit charge, and so it's just EX. So the change in potential energy from one place to the next is negative of the electric field times the distance between those two spots. Okay. And so units, what are we looking at here in terms of units? This is important, because this is your guide to a lot of things. A volt is a joule per coulomb. Remember, a joule is a Newton meter per coulomb. And if I have a Newton per coulomb, that's electric field. So Newton per coulomb times meters. And that's what we were looking at before, right? Voltage is electric field times the distance. Newton per coulomb, joule, Newton per coulomb meter is the same thing as a joule per coulomb. And then also, that means that a Newton per coulomb is the same thing as a volt per meter. So there's one of the sample problems that said an electric field was some quantity of, and then volts per meter. That's another set of units for electric field. Electric fields can be Newton per coulomb or volt per meter. So this is important. An electron volt. It's a unit of energy. Specifically, it's the energy that an electron or proton gains when moving through a potential difference of 1 volt. And so 1 electron volt, realize this is like coulombs times volts, is 1.6 times 10 to the negative 19th joules. Because I'm taking, if I multiply coulombs times volts, I end up with joules. So electron volt, you'll see that a lot when we're dealing with small scale things. We'll talk about electron volts. It's a unit of energy. And so then 1 kilo electron volt is 1.6 times 10 to the negative 16th joules. And then a mega electron volt is 1.6 times 10 to the negative 13th joules. That's a mega electron volt. And this is a kilo electron volt. So, example 1. Let's take a look. So initially the kinetic energy is 0, and the final kinetic energy is 12 electron volts. But I'm going to convert this because I want to see what this is in terms of joules. So this is 1.6 times 10 to the negative 19th joules for every 1 electron volt, right? That's how many joules there are in electron volts. And so this is 1.92 times 10 to the negative 18th joules. So what's the final speed? So what I do is I set this equal to 1/2 mv squared, 1.92 times 10 to the negative 18th joules. That's how much the kinetic energy has changed. Started with 0. And so I just set this equal to 1/2 mv squared. M is the mass of an electron, 9.11 times 10 to the negative 31st kilograms. So I take this, multiply by 2, divide by the mass, take the square root, and you should end up with V equals 2.05 times 10 to the 6th meters per second. 24.4, that slide, electric potential is, again, the potential energy per unit of charge, and a volt. 1 volt, again, is 1 joule per 1 coulomb. So if you take, it's the amount of energy gained moving 1 coulomb of charge through, rather you gain 1 joule when you have 1 coulomb charge go through 1 volt of potential difference. Okay, now electric potential and equipotential surfaces. Now we're talking about drawing diagrams, looking at electric fields, that sort of thing. Equipotential surfaces are surfaces consisting of a continuous distribution of points having the same electric potential. And the way they're related to E field lines, and this will make more sense, I think, when we do some drawings, equipotential surfaces and E field lines are always perpendicular to each other. So if I draw some electric field, let's say for a sphere, if these are the electric field lines, the equipotential lines are going to be perpendicular to the electric field lines. So that's perpendicular to that, perpendicular to that, perpendicular to that. And what we mean here is that everywhere along this line, along this surface, there's the same value of electric potential. Okay. And so then if I take a charge and I move it from here to here, no matter what path I take, out and away, out around this way, whatever, from here to here, no work is done because it's the same electric potential. It has the same electric potential energy. You go from one level to the next, and as a result, there's no net work done. One of the ways you can think about all of this is as a surface. So if you have a positive point charge, let's say we have a positive and a negative point charge, something like this, what does this look like? Well, if I were to make, this is high potential, this is low, we can make kind of like a topological map, where these are different altitudes. This is high potential, and so then the equipotential surfaces would be like these altitude references. And so then this is going in like this. So imagine having some positive test charge, you put it here, and it would accelerate there. It's like having a ball going here and then rolling down the hill over to that spot. And so then all of these lines are like places where the altitude is the same. It's like looking at a topological map. And we're going to see a map of something like this. We're actually going to create one using Excel as one of our labs for this unit. I think this is a helpful way. So then where's zero, right? Where is zero potential? An infinite distance away. You go an infinite distance away, and it levels out at 0. This is positive potential. This is negative potential. And that's on the next slide. It says electric potential. So V depends on the location in the E field only. wherever you are here, the voltage depends just on where you are in that field. And so then if you've got, for various geometries here, let me erase this so I can draw some of this stuff. So in a uniform electric field, again here, this is, here's the electric field. These are the equipotential surfaces. Notice they're perpendicular to the electric field lines. And as you go in the direction of the electric field, it's losing potential. So imagine you've got some positive charge over here, maybe negative charge over there or something, where this is a large sheet of positive charge, so it's creating this uniform electric field. And then the question here, it says if the distance between the equipotential surfaces in the top diagram are 1 centimeter apart. So the top diagram, it's like 20 and then here. So if this is 1 centimeter, it says what is the magnitude of the electric field? I guess it's referring to the this from here to here. So this is 1 centimeter, and this is a difference of 4 volts. Right? So EX, the electric field, times the distance, that's the voltage. So if I have voltage per distance, volt per meter, then that's going to give me the electric field. And so I've got 4 volts for every 1 times 10 to the negative 2 meters. And so that's going to end up being 400 newtons per coulomb, or volts per meter. And that's between these lines. That's 1 centimeter. Okay. Again, the next geometry for if you've got a point charge, then all of your equipotential surfaces are these spheres that surround the point charge. And notice here that that's because of the symmetry of a point and the circles, that those look like the Gaussian surfaces. When we were choosing Gaussian surfaces, what we were trying to do was choose equipotential surfaces. That was really the goal, even though we weren't saying that at the time. And so the little line there, equipotential surfaces are perpendicular to the electric field line. So that's kind of your number 1 rule. It'll help you see that. The next one, the dipole, the negative and the positive charge, that's like what I drew here before. And it looks like slope fields in math. We're going to see some of this stuff. At the end of this unit, there'll be a little addendum about the gradient operator. And so then, again, you can see what the equipotential surfaces look like if you have a positively charged sphere and a negatively charged plate next to it. They're off-center a little bit because of the charge distribution in the electric field lines. And some more geometries, just so you can see, again, what these look like. These look like these topological maps, where the lines indicate, various altitudes. And so, in general, let's take a look. There are 3 boxes on this page that we're filling in. This one, in general, the electric field is negative dV dr. Again, it could be R, it could be S, one of those things. So E is negative dV dx, something like that. In a uniform field, if it's uniform, then E is negative delta V, sorry, that's not velocity, we're talking about voltage. Delta V over delta X, or delta R, one of those things. And so again, thinking of this in terms of calculus, this then could be turned into E dx, negative E dx is dV, and so then negative integral E dx is dV, the way that these are related to each other. And again, if you use the units, that'll help you sort of put all this together. is this? This is a Newton per meter, or a Newton per coulomb. But if I have a Newton per coulomb and I multiply that by this, by x, then I end up with voltage per coulomb, or joules per coulomb. And so that's what a volt is. So we're adding more stuff to our units, but again, if you can keep it straight, that'll help you determine what these equations are. And again, the negative part here, this is like the relationship between work, right, work per charge, and change in potential, electric potential per charge. So let's see, calculate, example 1, calculating electric field from potential difference. So we already saw one like this. Based on the diagram there, what is the magnitude and direction of the electric field? We'll notice here that it's getting less. As you go to the right, the voltage is getting less. So that the direction of the electric field is to the right. And E is delta V over delta X. So this is negative 2 volts. And we're back. Okay, so with this problem, because it's a uniform field, right, delta V, and so negative 2 volts over, and this is 1 millimeter, so that's 1 times 10 to the negative 3. And so this ends up being, negatives cancel out. So this is 2 times 10 to the third newtons per coulomb, or again, volts per meter. Something like that. Example 2. Here you have a person standing, and it shows the electric field around a person. The person is in contact with the ground, and so we can call that 0 volts. They have a negative charge on them. And since this is relative, kind of like gravitational potential energy, we would just set 0 kind of where we wanted it. We're not dealing with distances at infinity here. So again, we're going to set 0 as the surface. The person is in contact with the surface, so they're grounded. And this is what happens when there's lightning. Surface charge builds up, and there's a charge building up in the sky, and then it discharges. So you act like a lightning rod, and this is part of why. One key thing you need to know here is that the difference between the top of this person's head and that electric field line is about 30 centimeters. Okay, so delta S is about 30 centimeters. Okay, so anyway, electric field then is again negative delta V over delta X. We're picking a specific point here, so we look at what's the potential difference. It is 200 volts from one surface to the next, or rather from the 0 up to the 200 volt line, because that's the distance. The point at the top of his head is roughly midway between, or the point of the 100 volt line, equipotential surface, is about midway between 200 volt and 0 equipotential surfaces, and there the 0 and 200 are 30 centimeters apart. So from 0 to 100, this is 0.3 meters, and so we end up with about 667 volts per meter. Okay. All right, let's take a look at example 3. And this is getting a little bit ahead of ourselves. So this is number 3. 12-volt battery is connected to 2 parallel plates. Later we're going to call these capacitors. The distance between the plates is 3 millimeters and is small compared to the size of the plates. That's to say that it's small compared to the size of the plates. That's important so we don't get these effects on the ends of the capacitor or the parallel plates, which we'll see. So we're imagining these as large sheets. And the reason for that is going to be something like this. We want the electric field to be these straight lines down that way. So this is connected to a battery this. This is 12 volts. So that's our drawing. And we want to find the magnitude and direction of the E field between the plates. So here's the electric field. Now the question is, what's the potential difference here? Well, if it's connected to a 12-volt battery, then you've got 12 volts from here to here. 12-volt potential there. And this is 3 millimeters. So V, let's just look at the magnitudes here. The magnitude of the electric field is magnitude of the voltage divided by the change in position. So this is 12 volts over 3 times 10 to the negative third meters. So we're going to end up with, what, about 4,000 newtons per coulomb. So this is part A. Part B, the change in potential energy when a proton placed at the positive plate is displaced by 1.5 millimeters. And so remember that work is equal to change in kinetic energy, which is equal to the negative change in potential energy. Work, again, FD cos theta. And so this is E, Q, X. Cosine of theta is 1, so we're going to leave that out. EQ is this, X is the D. And so we plug our numbers in. We have the electric field. The charge is 1.6 times 10 to the negative 19. And X is 1.5 times 10 to the negative fifth meters, or third meters. And I think you end up with negative 9.6 times 10 to the negative 19 joules. This is what we're talking about here. And let's see. All right, so next one, C. We want to know the speed of the proton after it's been displaced. Well, if this is the change in the potential energy, it starts at rest. So U at the beginning, or delta U, the change in potential energy, is going to be equal to the kinetic energy at the end, because it ends up moving. And so I already know this. So delta U is 1/2 mv squared. I won't write out all the numbers for this, but you can try it. That's delta U. M is the mass of a proton, which is 1.7 times 10 to the negative 27th. So this divided by that, multiply by 2, take the square root. And I think you end up with 3.39 times 10 to the fourth meters per second. And then D. D is saying, what is the acceleration of the proton? So the quick way to do this is force divided by mass, right? Acceleration. The force is EQ, and M is the mass of a proton. So E we have from over there. Q is the charge on a proton, 1.6 times 10 to the negative 19th. And then M is the mass of the proton, which is 1.7 times 10 to the negative 27th. I think you get 3.8 times 10 to the 11th meters per second squared. That's a pretty big acceleration. And that's it for that first section. Are you guys paying attention over there?